So let's look at the fundamental theorem of calculus. Let's say we have a function f of x. If it's continuous on the interval, closed interval a through b, then we can say that a new function, capital F of x, is equal to the integral of f of x dx from the bounds a to b, and that's going to equal f of b minus f of a. And the capital F is the integral of the function, so the antiderivative. And what this basically calculates is the area in the bounds a through b, because integration, when you find the integral of something, you're finding the area under the curve. Also, we can say that if we have bounds a through b of f of x dx, we can swap the bounds and put a negative sign. So we can also say negative b through a f of x d of x. Okay, let's look at question 1 here. So it says, evaluate the definite integral of x cubed dx from the bounds 0 through 1. So to solve this, let's use the fundamental theorem of calculus again. So we know that the theorem states that if we have a function f of x, capital F of x, and we set it equal to the antiderivative of our function, which is x cubed dx, and you should also notice here that we don't have bounds because we're only simply finding the antiderivative. We're not finding the area yet. We're only going to find the function that we use to find the area. So that's why we don't have bounds, because this is an indefinite integral which has no bounds. Okay, so if we just use the power rule on this, we'll get x to the 4 over 4 plus c. Even though we have a plus c here, we're just going to ignore it for now because we're only finding the area and we're not finding the actual function itself. So we're only going to look at x to the 4 over 4. And we also know our bounds are 0 and 1. And the theorem also states f of b, which is 1, minus f of 0, or minus f of a, which is 0, is equal to the area. So let's just write that out. 1, 0, x to the 3 dx equals f of 1 minus f of 0. Now let's substitute 1 and 0 into our new function, which is, if we plug in 1 into this, we'll get 1 to the 4 divided by 4, minus, if we plug in 0, we'll get 0 to the 4 divided by 4. Now if we simplify this, we'll get 1 to the 4 is just 1, divided by 4 is 1/4, minus 0 to the 4 is 0, and 0 divided by anything is always 0. So this just goes away, and we're left with 1 over 4. And since units aren't mentioned, we can just say this is units squared. And that would be our final answer. So the area under the curve of the function x to the 3 from the bounds 0 through 1 is 1/4 unit squared. Okay, let's look at question 2. We have evaluate the indefinite integral of x squared plus 3x plus 2 dx in the bounds 1 to 3. So once again, let's use the fundamental theorem. So first let's find our antiderivative, and we'll set that equal to f of x. So our antiderivative of x squared plus 3x plus 2 dx, and now we can use a power rule for every single term. So this is going to be x to the 3 divided by 3 plus 3x squared divided by 2 plus 2x plus c, but we're just going to ignore it. Okay, so now we have our bounds 1 and 3. So let's just find f of 3 and f of 1. So f of 3 minus f of 1 equals, okay, now let's plug in 3 in this first. So let's put parentheses. So we have 3 to the 3 divided by 3 plus 3 times 3 squared divided by 2 plus 2 times 3, and we're going to ignore the plus c. And now this is going to be subtracted by 1 to the 3 divided by 3 plus 3 times 1 squared divided by 2 plus 2 times 1. Now, we can evaluate this by hand, but it's a lot easier if you just plug into your calculator. And once you do plug this into your calculator, you will end up having 74/3 and units squared. And that is the final answer. Question 3, we have evaluate the indefinite integral of 1/√2x minus 3 dx in the bounds 2 to 6. So first let's find the antiderivative, which is f of x equals the integral of 1/√2x minus 3 dx. And this is going to be equal to, well, first let's manipulate the function a little bit. So since it's 1 over, and we know square root is the same as to the power of 1/2, we can write this as 2x minus 3 to the power negative 1/2. Now this becomes a lot easier to simplify, because from the rule of integration of f of ax plus b, we know that this is going to equal, if we take a and find the reciprocal of it, this is going to be 1/2 times, now power rule of the entire function, so we take the original function again, 2x minus 3, negative 1/2 plus 1 becomes 1/2, and we divide by our new power, which is 1/2. Now let's simplify this whole mess. So dividing by 1/2 is the same as multiplying by 2. So this and this gets canceled out. And we're just left with the square root of 2x minus 3. And this is our new function, plus c. But we're just going to ignore. So this is our new function, square root 2x minus 3. Now let's find f of b minus f of a. And we know b is 6, a is 2. So f of 6 minus f of 2. And this is going to equal the square root of 2 times 6 minus 3 minus the square root of 2 times 2 minus 3. And this is going to equal 2. And 2 units squared. And that is our final answer. Let's look at question 4. Evaluate the indefinite integral of cosine x dx in the interval 0 through pi over 6. So now we're looking at trigonometric functions, and let's look at the antiderivative of that. So since it's a cosine function, or a trig function, we can't really use a power rule anywhere, but if you remember how to derive trig functions, you know that the derivative of sine x is cosine x, so that must mean the integral, which is the opposite of derivatives, the integral of cosine x is sine x. So there's just formulas out there where you just have to remember them, or if you can't, you just have to know how to derive them. But yeah, so the antiderivative of cosine x is equal to sine x plus c. Okay, so we have our function, our new function, f of x, and let's find f of b minus f of a. So f of b, which is pi over 6, minus a, or f of a, which is 0. Okay, so now let's plug in pi over 6 into sine, because we're ignoring plus c. Sine pi over 6 minus sine 0. And now this is going to give us, if you remember your unit circle, sine pi over 6 will give you 1/2 minus sine 0 will give you 0. So the final answer is 1/2 units squared. And that is the final answer. So no matter what type of function it is, as long as you remember the fundamental theorem of calculus, you find your antiderivative, and you plug in your bounds, it will work for even trig functions and all types of other functions. So this is the final answer. Let's look at question 5 here. We need to evaluate the definite integral of e to the 1 minus x dx from the bounds 4 to 2. And one thing you could recognize here is actually that the lower bound is greater than the upper bound. 4 is greater than 2. So we can still evaluate the area using the fundamental theorem of calculus, but what we would need to do is use the reversal rule, where we need to add a negative sign and swap the bounds so that 2 becomes the lower bound and 4 becomes the upper bound. And we want to do this because we want the upper bound to be greater than the lower bound. Because when we do that, we calculate the area under the curve from left to right. But here, since the lower bound is actually greater than the upper bound, we calculate the area from right to left, which is why we need to add the negative sign. Also, when we interpret the area of a definite integral, we need to keep in mind of the Riemann sums, because the definite integral is just nothing but the Riemann sum, except that there's infinitely many rectangles. So Riemann sums are just a bunch of rectangles under the curve to give an approximation of the area, and this integral sign just means that there's infinitely many of those rectangles. Okay, now let's actually solve the area under the curve. But first, let's use a reversal rule that we talked about before. So let's rewrite this integral. Since we have 4 to 2 of e to the 1 minus x dx, this is going to equal, if we just swap the bounds and add a negative sign, it will be the exact same. So 2 to 4, e to the 1 minus x dx, the exact same function. And now what's actually interesting about e to the x is that if you remember with derivatives, the derivative of e to the x is the exact same function itself, e to the x. Similarly, the integral of e to the x is also e to the x. But just because it's the same doesn't mean we can still use rules to evaluate when it's not just e to the x, because here we have 1 minus x. So what do we do there? So let's find it. F of x is equal to the antiderivative of e to the 1 minus x dx. And if you see here, this is this is written in the form ax plus b, or I guess in this form, b plus ax. And here, a is negative 1. Even though you can see, it's 1 minus 1x. So the reciprocal of a, which is negative 1, 1 over negative 1 is the same thing. So negative 1. Negative e to the 1 minus x plus c. We're just going to ignore, but we have our function. F of x equals negative e to the 1 minus x. And again, this is just a formula that you're going to have to remember how to integrate logarithm functions, exponential functions, trig, all that. You're just going to have to remember some of those to find some definite integrals. Okay, now let's find f of b minus a. And again, we have b as 4 and a as 2 because we use a reversal rule. But also, we need to keep in mind that we put a negative sign, so we can't ignore that. So let's do it over here. Negative. And then f of b is e to the 1 minus 4 minus, negative sign there, negative e to the 1 minus 2. And now let's simplify all this. This is going to be negative e to the negative 3. Negative negative becomes a positive e to the negative 1. Now let's multiply the negative by both terms, and we're going to get e to the negative 3 minus e to the negative 1. And if you plug this into a calculator, you're going to get something around negative 0.318 units squared. And that is our final answer.